Our very last topic in solids, I'm going to randomly take us into this chapter 9.6. So chapter 9, section 6, subsection 5, metallic bonds and conduction bonds. Why this is not in chapter 12, I have no idea. But in any event, I was talking about conduction with graphene in that previous video. So I want to expand on that a little bit and talk about semiconductors, okay? Which is how this whole brand new technological world is going round. And if you don't know what a semiconductor is, hopefully after watching this video, you do know what one is and you recognize that they are everywhere all around us. It's what makes this thing work. It's what makes my computer work. So let's get into it. So first, before we talk about what a semiconductor is, let's talk about band theory. So band theory is an extension of molecular orbital theory that describes bonding in solids. And so if you don't remember what molecular orbital theory is, this is just an extension of atomic orbitals to give us the orbitals of molecules. Okay, and I mentioned, sp3, sp2 hybridizations, right? That's what we get from our molecular orbital theory. All of these hybrid orbitals. Okay, so within band theory, we talk about two different types of bands in metals. So that's the valence band, and that's a band of orbitals that are filled or partially filled by the valence electrons. Right? So that's no different than when we do our Lewis structure and we count up the valence electrons. But now we're dealing with metals, right? So these are not covalent bonds. Okay. So, and then there is the conduction band. And so in metals, this is an unoccupied band at higher energy than a valence band in which electrons are free to migrate. So often metals are described as having a sea of electrons. Not only can I not write, but I can't spell. Sea of electrons. So in other words, when we think about a network of metals, okay, or even any type of metallic solid, sorry, I keep hitting my little desktop thing. So electrons are free to flow through metals via this conduction band. That's what gives metals their conductive properties, is that they have this unoccupied set of orbitals that's like a little highway for electrons. So I'll note that the conduction band, we'll also call it an electron freeway. We're in California, right? We invented freeways in this state. The electron freeway. Okay, so if we kind of expand on this idea here and think about what our interacting atomic orbitals would look like, if we have just simply two orbitals, two singular orbitals, they're going to be well separated in energy. Okay, doesn't matter how much energy they're separated by. We can say that they are quantized. It's going to take a certain amount of energy to get from one to the other. And as we add 4, we can see it gets a little more complicated. 16, it gets even more complicated. And you notice that they're getting closer together. But now if we make a wild jump here from 16 to 1 mole, those lines become so tightly spaced together that it makes this continuous band. Okay, so that we could view that as our valence band or our conduction band. And if we kind of zoom in here, for example, let's suppose we have this set of magnesium, for example, or any other solid, right? We have recognized now the atoms are just kind of lining up. And we know that we can make layer upon layer upon layer of atoms. And if we were to zoom in to a handful of these, we can see here, these are the nuclei, okay, where the protons and the neutrons are. And here now we can see our atomic orbitals, 1s, 2s, 2p, etc. And as we go higher up on those scales and get to the valence band, so that's the filled molecular orbitals, so that's valence. And so, for example, our magnesium right here, that would be into the 3s level. So you can see here's magnesium, 1s, 2s, 2p, 3s. And so there's our 3s layer. So there's our valence electrons. Now, if we go to the very next layer above magnesium, 3p, it's empty. And that would represent our conduction band. And if we were to, make a wire out of this thing and plug it into a wall, this is where our electrons are going to flow through. They're going to flow through that empty molecular orbital that we know as the conduction band. Okay. So now if we look at things that are really good conductors, so magnesium is not that great of a conductor. Zinc, much better. So our transition metal elements, our true metals, right? Those are very good conductors. And the reason for that is because they actually have this overlap between the valence band, which we recognize is filled, and the conduction band, which we recognize is empty. Okay. And once again, this is also showing us, right, if we had one zinc, it'd have a pretty simple orbital diagram. If we have two zincs, the levels, we can see two levels now. If we had 4 zinc atoms, the levels are getting closer together. And of course, the zinc N, where this N now corresponds to Avogadro's number, 6.022 times 10 to 23, or something close to that number, right? So in other words, we have, a macroscopic quantity of zinc atoms. We now have this completely filled band, right? This continuous band of valence electrons. And we notice here with zinc, right, if we follow it through, it's got the 4s, 3d, and then the next one over is 4p. So here we can see all of our 4p electrons for zinc. So this would be for one zinc atom. And as we move over and over and over and over, we're getting to that 1 mole of zinc atoms. And you can see, if we were to zoom in on that, there's many, many, many levels, but they're all basically smashed together. There's overlap here. And what that means with that overlap is the electrons and zinc can easily go from the valence band to the conduction band and flow through the material. Okay, so that's what makes this a good conductor. So good conductors have this overlap. So I talked about graphene being a superconductor. So that means it has an even better overlap than is pictured here. Okay.